Okay, so today, guys, we are going to go through some wave notes rather quickly because of what we did over the past 2 days. And then we are going to work through some of these concept builders. All right, so if you pay attention to the notes, this will help you through the concept builders that we're going to do together. All right, so we got our waves. Yeah, you guys probably want to have this open because this will help you guys during the concept builder as well. All right, so waves are disturbance that transfer energy. Source of all wave motion is vibration. They carry energy from one place to another. They don't transport matter. So like, let's say a particle out of my mouth when I'm talking, it's a sound wave, right? That particle doesn't go from my mouth, that single particle, all the way from my mouth to your ear. What happens is it hits into another particle and they collide and basically ricochet down a line, almost like a dominoes, if you would, all right, to whatever source we're talking about. So like the whole, like that first domino that's not the one that reaches your ear. It's one that's like right next to you. Mechanical waves require a medium to go through. Medium, solid, liquid, gas. All right, we have sound waves, water waves, spring, slinky, rope, electromagnetic waves. These guys can travel without a medium, all right, so through space, and they move wicked fast. Wave structure, you got to know this one inside and out. All right, the tops are crests, the bottoms, troughs. Wavelength is one complete cycle. So you can do wavelength one of two different ways, or there's more than that, but crest to crest is usually the easiest, but also where you start, right? You see how it starts right here on the on our resting position right there. So if you go from that spot 2 times over where it crosses, so this will be the first time it crosses the middle port, and then the second time. So it's the second time, all right, after the first spot, the second time it crosses, that would be one complete wavelength. So you have this whole top, bottom to bam. So that would be that one complete wavelength there. And then amplitude. Now, amplitude is the resting position. So that middle position, equilibrium, to either the top of a crest or to the bottom of a trough. So you need to know those ones ins and out. Okay, medium, yep, material through which they're traveling through. In these mechanical waves, they're going to gradually lose energy to that medium, which would make sense because if you're 400 yards away from me and I'm talking at this level, you're not going to hear me at this level. Eventually, it's going to lose a lot of that energy due to collisions, heat, all right, other different, we got a couple of different other things that happen, and the wave, the energy kind of dissipates. So examples, water, sound, rope, spring waves. Mechanical waves are classified by how the medium vibrates. So a pulse is going to be the direction the energy is moving it. Now, a vibration is going to be the direction of these particles relative to the pulse. So a longitudinal, let's say the energy is straight out, the particles are moving in that direction, straight. They're parallel with it. Okay, so if the energy is moving to the right, the particles move parallel with it to the right. Where transverse, they're perpendicular. So if the wave is moving to the right, okay, it's going to probably be up, and the particles would go up and down. Longitudinal, all right, yep, talks about it here. So parallel to the pulse of a wave, transverse wave, perpendicular to the wave pulse. You guys, these will be questions on your quiz and test. These will be questions on your quiz and test. So this will be something you want to make sure you have open, okay, during. Transverse wave, again, perpendicular, can be sideways or it can be up and down. Electromagnetic waves, light waves are definitely transverse. Longitudinal, again, parallel, back and forth we have a compression and rarefaction. Compression are where the particles are packed closely together. Rarefaction will be an expansion, like the spot where it's a little bit, all right, more spaced out. The most common example is a sound wave. Okay, these characteristics, this will be again asked in the concept builders. So the amplitude can be from the resting position to a crest or resting position to a trough. So I'm going to show this real quick. Right here, from here to the top, that is a, I don't know why, let's do a different color real quick. Let's show the red. Okay, so from here to here, that would be an amplitude. Not if I went from, all right, you see how this is dashed out? From here to the bottom. So from crest to trough, that is not an amplitude. That is not an amplitude. The amplitude is just going to be, all right, from the resting position or equilibrium position to either a crest or from there to a trough. All right. Now, wavelength would be the distance between two consecutive parts of a wave. So if I started here, the second time it crosses the middle point again. So this would be 1, this would be 2. So that is a complete wavelength. The easiest way is usually going to be from crest to crest. That is usually the easiest way to figure that out. But it could also be from trough to trough if you're looking at a longitudinal wave, compression to compression, or rarefaction to rarefaction. Wavelength, the symbol is lambda, which is basically like an upside down Y. Looks like that. That's the distance, all right, between any two consecutive points on the wave. And then velocity, all right, lowercase v in this case. All right, speed, how fast this wave travels. Guys, how do you calculate speed? Anyone? Anyone remember how we calculate speed? If I asked Joe how fast you are, if I said go run, how are we gonna calculate how fast he's running?
Distance over time.
Distance divided by time. Miles per hour is a unit. Meters per second are units that we would use. All right, very good. So amplitude, this will give the indication of power or strength of this wave. So if we're talking sound waves, like something that's quiet has a low amplitude. But if it's louder, the amplitude would be much higher. Same thing goes with light for brightness, right? Like your phone has like the little flashlight app, and like there's like levels you can hit it, like dim, and then you can like increase the brightness to it. All right. Even though they're the same frequency, same wavelength, the amplitude is jacked up, all right, when it's brighter. Wavelength, symbol lambda, distance between any two repeating points on the wave. All right, we talked about that as well. This can help determine what kind of colors we see or what notes we hear in music, all right, for pitch. The shorter the wavelength, all right, the more cycles per minute. So like if you think about it, I guess like this. All right, so if you're thinking about wavelength, something that's oscillating up and down. If that's the case, okay, if the wavelength is long, all right, it's not going to happen as often. The frequency is not going to be as great. So wavelength and frequency are generally inverse of one another. Next one. Okay, velocity, the rate at which this energy travels, speed and direction, depends on the medium. So for mechanical waves, they are going to travel faster in more dense mediums. So if you tried hearing a boat in the ocean with the motor going, you would be able to hear it underwater first before you would be able to hear it on land. It travels faster. So the more dense the medium, the faster it travels. That's mechanical wave. So think like mostly we would talk probably like sound. So sound, why that happens is because the particles are closer together the more dense the medium. All right, and they can do that kind of collision thing and move around, pass through at a quicker rate. Electromagnetic waves like light, that's different. They're going to travel slower in more dense mediums. So light travels slower moving through, let's say, water than it does through air. Okay, here are two formulas, guys. This is what you want to look at and pay attention to. All right, you're going to want this open for our assignment. Velocity of a wave, V. All right, meters per second. Frequency we measure in hertz, capital H, lowercase z. Lambda for wavelength, measured in meters. But also, speed can equal a distance divided by time. Okay, so you'll have those, you have your two triangles. Frequency. Pay attention to this because this will help us on several of these concept builders that we're going to do today. Number of wavelengths that pass any point per second, measured in wavelengths per second, cycles per second. If you went like this with your lips, and it said, okay, your lips move back and forth 120 times in 1 second. Well, how many wavelengths are cycles? Well, cycles would be there and back, right? So the vibration of your lips said you did 120 per second. So the frequency would be 120. If it said it did that many 120 in 2 seconds, well, then you would divide it by the total time right there. So it would be the cycles divided by the time. 120 divided by 2, then our frequency would be 60. Hertz is the number of wavelengths, okay, that go through a spot in a per second. And frequency is related to a velocity, again, via the triangle. If I had to cover up F, if I wanted frequency, I would need velocity and wavelength. So I would do velocity divided by wavelength in order to get frequency, which you'll need for your assignment. Period. The amount of time it takes for one cycle or one wavelength to pass a point. And it's inverse to the period. I'm sorry, it's inverse to the frequency. So if you know what frequency is, all right, you're just going to do 1 divided by that to find period, or vice versa. Okay, you have some sources. So we're going to go through some of these guys. It may go a little bit quicker, but let's get on this. So guys, I'm going to just kind of call on you, or please volunteer. All right, guys, everyone try to participate in this because this is going to make you better at it. If you're not, it doesn't, okay? Okay, 2 truths and a lie. I love that game. All right, but here we're working with frequency and period. Period and frequency are inversely proportional to one another. Is that true, false?
You're making a false face.
I'm not making a false face, your face. What? Related inversely. They are inverse to one another. So for that reason, that's true. Period and frequency are reciprocals. That would be, yeah, it's basically saying like the inverse. Vibrating objects make many vibrations in a short amount of time, have a long period. So the more often it's going, right, the faster or the more vibrations it's going, the less time it takes to do a there and back. So like if I were to show this. So if you're doing like a there back motion, all right, this is a low frequency because it's not happening super often. But if from top to bottom, back to the top, that would be 1 complete cycle. It takes a longer period of time versus if I went like this. In this case, the frequency is very high, but the time has gotten smaller. So we would say 3 is the lie. Next. A vibrating object with a high frequency has a vibrating object has a large distance. Moves a large distance in a short amount of time. Not really sure. Vibrating object with a high frequency would have a low period. That's true. Vibrating object with high frequency undergoes a relatively large number of vibrations in a short period of time. Does that make sense? Yeah, so I'm thinking 2 and 3 are true. I'm thinking 1 is the lie. Do you agree? That away. All right, let's try one more on these and we'll scoot. The period refers to the distance between 2 extreme locations along a vibrational path. I don't remember that in the notes. A vibrating object with a large period takes relatively a larger amount of time to make 1 vibration or 1 complete cycle. That definitely is true. Period relates to the amount of time to complete one. Yeah, that's true. Is also 1. You're the liar. Nice. All right, let's go back to the main menu. All right, let's do some case studies right quick. Oh, this is dope. This is super easy. All right, guys, everyone look at this. Look at these diagrams. Looking at these two, which one has the greatest period? Period would be the time it takes to complete one cycle. What do you think?
A.
Why B?
Because they're more spread apart.
Because they're more spread apart and time is down here. So, all right, if we said one wavelength is from crest to crest, okay, it takes, yeah, there's a longer distance in between them than over here. Another way you can think about it is the one that has a higher frequency has a shorter period. And A is happening more frequent. So let's see, we were going to say B, right? Next. Okay, frequency. Which one is going to, how do we find frequency? Frequency would be number of vibrations per time. So if we did the first one, what is 10 divided by 16.2? That's 0.61 and change. And then we have 10 divided by 13.8, 0.72. So case B has a greater frequency. How did I find that out? Yeah, the number of cycles per second. How many cycles did we have? 10 divided by the time. So, yep. Which one has the greatest frequency? A, yeah, it's happening more frequent, if you will. Haha, terrible joke. Relax. Yep, so what? Leave me alone. Okay, which one has the greatest period? So to find period, it would be the opposite. The number of time it takes, the total time it takes to complete all cycles.
B.
In this case, yes, it would be B. 13 divided by 10, 1.38. 10 divided by 16, 1.62. Yep, that's going to be the one that takes longer. All right, now let's go. Great. Let's go back to the main menu. Let's try do the math portion real quick. Okay, if you make 5 back and forth vibrations in 13 seconds, what is the period? How do we find period? Total time divided by the total cycles. So what would I do? 13.5 divided by 5. All right. So we can even justly say total time divided by total cycles. And so 13.5 divided by 5, that leaves me with 2.7. And what would my unit be for period? Is it meters per second? Hertz, seconds, meters per second, hertz, seconds. Yert. Next. Okay, the kid makes 5 back and forth swings in 18 seconds. What is the frequency? Well, what is frequency? The number of what? Cycles per second. How many cycles did you have? 5 back and forth cycles or vibrations in the total time. So we would do 5 divided by 18.5. That comes out to be like 0.27, and the unit for frequency is hertz. Everybody cool with that? All right. How would I do this one? What do they want? Period, right? So how would we find period? Yep, total time divided by total vibration, so 9 divided by 36, okay? All right, cool, so we got those. Now, let's do these guys. Some of the wave basics. Okay, let's start this real quick. Two truths and a lie. A wave moves through a medium because particle A pushes on particle B, which pushes on C, which blah, 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 continues. That's true. When a wave moves through a medium, particles of the medium move along an undulating or curved path from one end to another. Not really sure. A wave transports energy from the source to a distant location. All right. Which one to be thinking? You think this or number two? Number two? I think so. Good call. All waves are created by vibrating objects. That's 100% true. A fast wave is a wave that causes the particles of the medium to move quickly from one end of the medium to another. Not sure. When a mechanical wave moves through a medium, the particles of the medium vibrate around a fixed position. This is going to be the lie, and the reason is because the way this is worded, it's saying like a particle, let's say from my mouth, right? Think about a straight line path of dominoes from myself to you, right? And I tip over the first particle as I make a sound. That first domino is not going to be the one that reaches your ear, right? So that's kind of what this is saying. They're saying, oh, well, these particles go from one end to the other. No. Nope, don't want directions. Thank you. Let's go to main menu. Let's go to this one. This is great. Matching pairs. All right. Give me a first one. Give me one of these. Guys, this is like Jeopardy. All right, pick a mechanical. All right, so if I said electromagnetic wave, what is the definition that goes with it? Remember, this is why I said you can have this guy open. So if I wanted to like scoot back, electromagnetic waves. Okay, we talked about those somewhere. Electromagnetic waves can travel, all right, at the speed of light without a medium. Let me see, does that help? Correct, it is the one under it. It can move through a vacuum. Okay, what about a mechanical wave? Okay, energy is transferred by vibrations through a medium such as a solid, liquid, or gas. Okay, so which one? Bam. The one under it? Longitudinal wave. Is that parallel or perpendicular? Good, parallel. And then transverse are the ones that are perpendicular. Bam, we got our trophy. Okay, here, guys, we need to identify, all right, a couple different things. This one is a real pain in the butt. Each guy here is 1 centimeter long. So if that is the case, all right, if we started at 1 compression here, from 1 compression to the next compression, all right, it's going to be 1, 2, 3. Okay, here they want us to figure out what are each of these guys. Okay, so at point A, what do we call that? If this is a longitudinal wave. So again, have this open, guys, so you can help me out with this, please. Longitudinal wave, we got this piece here. So what would point A be? Is it a crest? Is it a trough? Is it a compression? Or is it a rarefaction? A, compression. B, yeah, that would be a rarefaction, where it's like fartherly spaced apart, and then the other two will obviously. Whoop, almost messed that one up. Next. Okay, the amplitude. So from the center to the top of this guy, how many boxes are there? 1, 2. So the amplitude would be 2. All right, wavelength. That's a pain in the ass. We could do from crest to crest, or we can do, excuse you, from this starting position, right? And then 2 more times it goes through. So not here, but here. That would be one wavelength. So how many boxes we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. Boom. Shaka laka laka. Okay, this guy's real quick. What is A? Crest. B. C. Drop. Yep. D. Yep. Ain't no thing but a trick in my. What? Oh, I didn't. That was my fault. Okay, next. Come on, come on, come on, come on, come on. All right, definitions. Let's roll through. Roll through. Speed would be what? Let's check it. What about amplitude?
Distance from real position.
Good. Wavelength. And then frequency, number of cycles, all right, per second. Solid. All right. Conceptual meanings. Speed would be what? Good. What about amplitude?
How high?
Good. How high? Wavelength.
How
Right. We went to, where's this? Transverse wave. Wavelength would be like how long. Amplitude is this dude. So then let's go back. So wavelength would be how long. And then frequency would be how often. Trophies. Trophies. Okay. Dang. What do we got? Speed. Speed would be what? Good. Distance divided by time. What about amplitude? Good. Maximum distance, all right, on the medium displays from rest. So that'd be like from the middle to either the top of a crest or the middle to the bottom of a trough. Frequency. The number, and the period is the number total time divided by the total cycles. Skr, skr. You guys are on fire. Okay, let's see if you know these units. Speed should be the easiest one. Yep, we've been doing that all year. All right. Hertz. Correct. Good. Period of seconds, ba-bam, and then wavelength in meters. You guys are studs. All right, bro. Let's see if you got these symbols, dog. Speed is F? You sure?
No.
You're not sure? Are you sure? Let's check it. Okay. Speed is V. Good. Frequency should be kind of obvious. Yeah. Period is T, and lambda is wavelength.
What's that called?
It's called lambda.
Looks like an
Mm-hmm. Okay, good. So we got through those. Okay, guys, so we're going to open up our, all right, describing waves assignment here. So we have a wave. All right, what they want to do is we want to put the letters of the correct guys in spots. So what letters are crests? B and E. Okay, boom. Put B and E here. What about troughs? D and, all right, and then neither, that would be everyone else. So that would be A, C, F, H, I, and J. ACF, HIJ. Yep. That'll be correct, sir. Okay, guys, real quick, what letter here gives me wavelength? All right, bet. A, very good. And what about the amplitude? Not B, because remember, amplitude is from resting position to a crest. So it'd be D. All right, it could be rest from crest or rest to trough. So yes, D would be the correct piece here. Okay. All right, so this one is a little bit of a funky doodle, but all right, they want us to measure wavelength here. So if we start here,
Wait, how do you draw?
you can't.
Huh.
It's a thingy that I downloaded. Don't worry about it. So if we start here, not at a crest, normally we could, but then we're not at like the starting point. It's a pain in the butt to measure. So if we start here at 0, right, the next, it's the 2 times it crosses it later. So 1, 2. This would be where we would draw our line straight down. And what is that at? 3 point, this is 5, 6, 7, 8. So we would say 3.8, right? Give me this. 3.8. It's in centimeters. What about the amplitude? How would I measure that? I could go resting position to the crest, but that's again, we're starting at a different number. That's a little funky. So I'm going to say let's start at 0 and then go up to, because that's where the trough starts, and go straight across here. What is that at? This would be 0.5, 6, 7, 8. So this one would be 0.8 centimeters. Number of cycles per period, what do we call that? I'm sorry, number of cycles per second or period of time. Frequency, good. Okay, let's get rid of all that. Any repeated motion can be described by frequency. So for instance, the frequency of rotation of a second hand on a clock. So how many, if a clock starts up at 12 and it goes all the way around, the second hand clock, that's just one complete rotation, right? That's one cycle. How long did it take? So you would do what divided by what? 1 divided by 60. So that would be your frequency. So it would be this guy here, A. Okay, a pendulum makes 40 vibrations in 20 seconds. How do we find the period? Period would be total time divided by the total number of seconds. So how much time did it take?
1-20.
20 divided by 40, which is 0.5 seconds. What? Well, frequency is the number of cycles per second, right? So it'd be 40 divided by 20. So the frequency would be 2. And since period is the inverse of that, if you did 1 divided by 2, that equals 0.5. This is just the shorter way of doing it.
Gotcha.
Number 7, Olive accompanies her father to a park where they're on a swing, motion characterized by a complete back and forth cycle every 0.5 seconds. That statement provides info about what? If it does 1 cycle in 5 seconds, what would that be?
Frequency.
Period.
It could be, but we're looking more for period here, even though you could find the frequency from that. All right, because it's telling you it's completing 1 back and forth motion every 5 seconds, that would be more so a period. Okay, so what would the frequency of that person be? Well, frequency is equal to 1 over the period. So 1 divided by t. So 1 divided by, what was the period? 5. I hate when it does that. 1 divided by 5 equals 0.20 hertz. So letter A. The period of a 5-second thing corresponds to a frequency of what? Well, we just did that, so this one would also be letter A. It would be done the same way. 1 divided by the period would equal a frequency, so 1 divided by 5, we still get this 0.20. How do you find, all right, the period of this guy? So T is equal to 1 divided by the frequency. If the frequency is 261, you would do 1 divided by 261, which equals 0.00383 seconds. As frequency increases, what happens to the period? Remember, if something is going back and forth faster, how long, the time it takes to do it 1 back and forth, does that get bigger or smaller?
Smaller.
Yeah, smaller, so it's going to decrease. The speed of the wave. How much time it takes to vibrate back and forth? No. How high? No. How often? No. How far a given point, such as a crest, travels per unit of time? Yerp. Okay, the two equations. Just write out this word.
You want to give these to work with?
So, because it's a pain in the butt, guys, for you guys to write the letter lambda out, you can just say V equals frequency times wavelength instead of writing that symbol. All right, because then you have to go to insert, special symbols, and or speed is equal to distance divided by time. Now, 14 says Macintosh are near the end of a swimming pool. They make a surface wave. The wave travels the length of the pool and back in 25 seconds. The pool is 25 meters long. What is the speed of the wave? So that surface wave goes to the end of the pool, which is 25 meters, and back, which is another how far? 25 meters. Okay, so it actually travels a total of 50 meters because of the there and back. So the 50 meters would be your distance, and the time is 25 seconds. So you get a final answer here of 2 meters per second. So a fisherman uses a sonic ranger to determine the depth of a lake. That sound wave travels at 1,210 meters per second through the water and requires 0.02 seconds to hit the bottom of the lake and back to the boat. How deep is the lake? So they want the distance. They want distance. We have speed and we have time? Well, what actually is going to be going on with this good is, all right, we have speed. We're not sure what the distance is. So we're speed times time. The time they give us is the time it takes to go there and back. But we want half that time because that will tell us the actual how deep it is. So because of that, you can do 1,210. You could do it times 0.02 and then divide by 2. Or what I did was I said the time was 0.01 seconds because that's how long it's going to take to go to the bottom. Either way you decide to do it, you're going to come up with that same answer. All right, and then the last one. Just want to hit the last one real quick so you guys have time to copy it down. Okay. So in the last one, they're telling us that this water wave moves at a velocity of 3 meters per second. So we have v. The distance from one crest to the next is 6 meters. So that's our wavelength. So we have velocity is 3, wavelength is 6. They want to know how much time is passing between each of these guys here. So if you solve for the frequency, which is your velocity over wavelength, you're going to get an answer of 0.5 hertz. But that's the frequency. They're asking the period between one to the next, and period is equal to 1 divided by f. So 1 divided by 0.05 is equal to 2 seconds. Okay?